everyone, and welcome to part 4 of our lecture, where we will be discussing the examples of metamorphism. So this is taking all the knowledge that you've got so far and looking at how it applies to real-life examples, so examples of metamorphism in the field. And as I mentioned in the very first lecture, this part particularly will be a pretty long lecture on its own. So we will be discussing 5 examples in total. So remember, if you need to take a break at any point within this lecture, feel free to hit pause, step away from your screen, and come back to it later. Because we have 5 examples, it's really going to take quite a while to properly get into it and discuss each example to do it justice. And therefore, if you need a break, remember you can take a break. Okay? All right. So let's move on into the next slide. So examples of metamorphism. So the classification, textures, and details of metamorphism in the following lectures, after mine are done, would be much easier to understand if we have a look at some of these examples of metamorphism. So bear in mind that the goal of practicing metamorphic petrology is to understand the physical conditions and the processes involved in metamorphism. And this will help us to interpret the condition and evolution of anything from metamorphic bodies to mountain belts to the Earth's crust. So in this particular section, we will be discussing the following examples from the Scottish Highlands to New Zealand to Japan to the Skiddaw Oriole in the UK, and also an example from Crestmore in California. So we'll be looking at why these specific localities are representative of the different types of metamorphism that they show. Move on to our very first example, which is the orogenic regional metamorphism of the Scottish Highlands. So in Barrow's area here, in the orange circle, George Barrow made one of the very first systematic studies of the variation in rock types and mineral assemblages with progressive metamorphism. So, metamorphism and deformation in the southeast highlands of Scotland happened in the Caledonian orogeny, where its maximum intensity was about 500 million years ago. It was so intense that we have the formation of naps, and the way that I used to remember this as an undergrad was that the rocks were so highly deformed that they had to take a nap. So anywho, the numerous large granites intruded towards the end of the orogeny, so this happens after the main episode of regional metamorphism. In this area, Barrow noted that there were significant and very systematic mineralogical changes in the pelitic rocks, so he found that he could subdivide the area into a series of metamorphic zones based on the appearance of new minerals in the rocks as the grade increased. So as the metamorphic grade increased, he found that he could divide the area based on the appearance of new minerals. So these new minerals that characterize any particular zone would be called an index mineral. So the minerals were listed as follows. So we have chlorite, biotite, garnet, andalusite, kyanite, and sillimanite. So the appearance of these minerals mark the new metamorphic zones as they move across the grades. And this specific sequence of zones now recognized, and the typical metamorphic mineral assemblage in each are as follows. So we have the chlorite zone, where the pelitic rocks are slates or phyllites that have chlorite, muscovite, quartz, and albite. Next, we have the biotite zone. So biotite zone, we have slates giving way to phyllites and schists. So going back, we have slates and phyllites here. Now we have phyllites and schists. With the following minerals. And we go further down, we have the garnet zone, where we have schists with red almandine garnet and the following minerals. So the index mineral here is garnet. So it's schist with garnet. And then we move into the staurolite zone, where we have schist, but this time with staurolite, and then schist with kyanite as you move away from that zone. And last but not least, we have the sillimanite zone, where it is an even higher grade of metamorphism, where you have schist and gneisses. So as you can see, there is a very specific sequence in which these minerals appear, and you can see that it happens with increasing grade of metamorphism. So we've gone from slate to phyllite, phyllite to schist, and schist to gneiss. So this sequence of zones has been recognized in other orogenic belts, and it's now so well established in the literature that these zones are often referred to as Barrovian zones, so named after John Barrow and Barrow's area. So the PT type conditions for this area would be called Barrovian type metamorphism, which is actually quite typical of many orogenic metamorphic belts. So Tilley, Kennedy, and some others confirmed Barrow's zones and extended them to a much larger area of the highlands. So if you remember, Barrow's zone was this small area here, and they extended it to a much larger area of the Scottish Highlands. So Tilley coined the term isograd, which is a boundary that separates the different zones of metamorphism. To summarize what we learned from this particular field example, we have an isograd, which represents the first appearance of a particular metamorphic index mineral in the field as one progresses up the metamorphic grade. So when one crosses an isograd, so if, for example, if you cross the biotite isograd, you're entering the biotite zone. So zones, therefore, must have the same name as the isograd that forms the low-grade boundary of that zone. So because classic isograds are based on the first appearance of a mineral and not its disappearance, an index mineral may still be stable in higher grade zones. So do take note that as you move further in studying metamorphism, you will come across an even broader category called metamorphic phases. But as for now, we're just discussing isograds and the appearance of index minerals as you move across metamorphic grades. So Barrovian zones have become the norm, to which we compare all other regional metamorphism areas. And this is an okay practice, so if you identify Barrovian metamorphism in other areas, it's okay to go, okay, so this is the sequence of minerals that we will expect, but it is important to note that we shouldn't let zones constrain our thinking and observations. So in case you come across an area and you're thinking, oh, after biotite is chlorite and after chlorite is this mineral, but you find a different mineral instead, you shouldn't let the zones defined by the Barrovian sequence to constrain your thinking or observations in your field area. And we can see how this would be important because there is a variation that occurs in an area just north of the Barrows study area, which is in the Banff and Buchan district. So the palitic compositions are similar as the ones we've seen in the Barrovian sequence, but the sequence of isograds here in particular, we see that it's chlorite, biotite, followed by cordierite, andalusite, and then sillimanite. So it's slightly different to the sequence that we've seen earlier. And this has to do with the stability of different minerals under different pressure and temperature conditions. So considering the following PT phase diagram for the system Al2SiO5, we have the three minerals, kyanite, sillimanite, and andalusite. And we also have on this graph is the hydration of Al2SiO5 to pyrophyllite, and this limits the occurrence of polymorphs at low grades in the presence of excess silica and water. So this limits the occurrence of polymorphs at low grades. So now our graph is pushed in this direction. So the stability field of andalusite occurs at pressures that are less than 0.37 gigapascals, and kyanite to sillimanite at the sillimanite isograd is only above this pressure. So what that looks like on the graph is, so stability field of andalusite occurs at pressures less than 0.37, so somewhere around here, and the change from kyanite to sillimanite happens just above this pressure. So here we have the change from kyanite to sillimanite. So with the Barrovian sequence, we had the transition from kyanite zone to the sillimanite zone, but with our Buchan sequence, we have it at a lower PT variation where it goes from andalusite to sillimanite. And this is because the geothermal gradient in this northern district is higher than in the Barrows area, and the rocks at any equivalent temperature must have been at a lower pressure. So this particular low PT variation has been referred to as Buchan type metamorphism. And this too is a relatively common thing. So Miyashiro, from his work in the Abukuma Plateau of Japan, also called such a low PT variant as the Abukuma type metamorphism. So these two terms here are both common in literature, and they mean essentially the same thing. So that was the Barrovian sequence. Let's now move on to our second example, which is regional burial metamorphism in Otago, New Zealand. So in New Zealand, they've got voluminous Permian through Jurassic sedimentation with intermittent volcanism. So what this means is that they've got greywackies, tuffs, and some volcanics buried in a deep trough that metamorphosed during the Cretaceous. So the fine grain size and immature nature of the material makes it highly susceptible to metamorphic alteration, and this happens even at low grades. And this particular area in Otago is the type locality of burial metamorphism. When people talk about type localities, they mean that this is the textbook example of burial metamorphism. So Combs and his colleagues showed that these low-grade rocks can be treated in the same zonal fashion as other regional rocks. So although the metamorphic grade reaches that of a medium Barrovian zone to the north, the lowest grades are of interest because it adds on to the Scottish examples that we discussed previously. So deformation and plutons are inconsequential in the area because basically the degree of metamorphism is directly related to the depth of the burial. So if you remember when we discussed the different types of metamorphism, burial metamorphism relies solely on the weight and the pressure because of that weight and the depth of the burial. So any sort of deformation and plutons, these are inconsequential in the area. So in this particular region, the isogrades mapped at lower grades are listed as follows. So we have different minerals compared to our Peruvian sequence because these are even lower grades. So we have zeolite, prehnite, pompelliite, chlorite, biotite, almandine, and oligoclase. So this in particular can be observed near the Haast River in Otago, New Zealand. And the cross-section XY, if we zoom in, we will see the different metamorphic zones of the Haast group, where we can see that it's divided into pompelliite, chlorite, biotite, garnet, and oligoclase. So orogenic belts typically proceed directly from diagenesis to chlorite or biotite zones, but the development of low-grade zones in New Zealand may reflect the highly unstable nature. So if you remember our rocks here earlier, they were unstable nature, they were unstable tuffs and greywackies. Plus the availability of hot water. So this further drove the metamorphism in this area, whereas if they were pelitic sediments, they would have probably not reacted until a much higher grade. The third example on our list are the paired orogenic metamorphic belts of Japan. So here we have the islands of Shihoku and Honshu, where a pair of metamorphic belts are exposed along the northeast-southwest axes parallel to the active subduction zone. So these belts are of the same age. So that sort of indicates that they developed together. So here in green, we have the Ryoke Abukuma metamorphic belt, and in blue, we have the Sambagawa metamorphic belt. So the northwest belt, or the inner belt, inward away from the trench, is the Ryoke, or the Abukuma belt. And this particular area, let's use green, so the Ryoke belt shows low PT Buchan type of regional orogenic metamorphism. So the area has dominant metapelitic sediments and isogrades up to the sillimanite zone. So it has a high temperature, low pressure belt, and granitic plutons are pretty common here. The outer belt, on the other hand, is called the Sambagawa belt, and this one is high pressure, low temperature nature. So it only reaches the garnet zone in pelitic rocks, and basic rocks are more common here than in the Ryoke belt. However, in these areas, glaucophane is developed. So this gives way to hornblende at higher grades, and the rocks here are commonly called blue schists. So basically, just to recap, our rocks here in the Ryoke belt develop high temperature, low pressure belt, but in the Sambagawa belt, it is a high pressure but low temperature belt. So the two belts are in contact along their whole length across a major fault zone, which is called the median line. So the Ryoke Abukuma lithology are similar to sediments from a relatively mature volcanic arc, and the Sambagawa lithologies are more akin to the oceanward accretionary wedge, where the distal arc-derived sediments and volcanics mix with oceanic crust and marine sediment. So those are the lithologies for the Ryokei-Abukuma belt and the Sambagawa belt. So the thermal model of a subduction zone system suggests that the 600 degrees Celsius isotherm could be as deep as the follows. So it could be as deep as 100 kilometers in the trench subduction zone and about 20 kilometers beneath the volcanic arc. So this is the 600 degree isotherm. So Miyashiro noted that the paired nature, so the way that we've seen that Ryokei and Sambagawa were paired together, was actually seen in different areas in the world. So coeval metamorphic belts, which had an outer high PT belt and a lower PT belt on the inside, ought to be quite common. So they've called this paired metamorphic belts. And these may be separated by 100 to 200 kilometers of less metamorphosed and deformed material. So we have this arc trench gap. Or it could be closely juxtaposed the way that Ryokei and Sambagawa was, where they were close to each other, separated by the median line. In the latter cases, the contact is commonly a major fault. So most of these belts are quite complex and they're not always coeval. What coeval means is that it's developed at the same time. So if we remember Sambagawa and Ryokei, it is inferred that it is coeval, but not all belts will be coeval. Number 4 on our list of examples is the contact metamorphism of pelitic rocks in the Skiddaw Aureole in the United Kingdom. So this would be found in the English Lake District, where Ordovician Skiddaw slates have been intruded by several granitic bodies, and these intrusions are quite shallow. In this area, the contact effects overprinted on an earlier low-grade regional orogenic metamorphism, where the rocks have been metamorphosed to chlorite zone slates, and outside of this aureole, the slates are tightly folded and they contain muscovite, quartz, chlorite, chloritoid, and opaques. As you would remember from our previous discussions on contact metamorphism, with contact metamorphism you would have an aureole forming around the igneous body. So the aureole around the Skiddaw granite was subdivided into 3 zones. So we have our inner zone, middle zone, and outer zone. And this is arranged in increasing metamorphic grades. So we have our unaltered slates, which has metamorphosed into the outer zone of spotted slates. We have our Andalusite slates and the inner zone of hornfells, closest to the Skiddaw granite. Let's go through the different zones one by one. So the first effects being 1 to 2 kilometers from the contact with the igneous body, we have our 0.2 to 2 millimeter size black ovoid spots appearing in slates. What this looks like, we'll have a look at it when we talk about the classification of metamorphic rocks, but basically what this means is that you have your slate, but it has protruding spots on it, which gives its name as a spotted slate to emphasize that it has these spots. So at the same time, recrystallization has happened and you have this slight coarsening of grains and the degradation of this slaty cleavage. So these spots here were probably either cordierite or andalusite, and they've since rehydrated and retrograded back to fine aggregates of mostly muscovite. So both cordierite and andalusite occur at higher grades, where they're often partly retrograded but not further out. So the spots that we see now in most of the spotted slates are probably pseudomorphs, and you will learn more about this in studying metamorphic textures. Next, in the middle zone, the slates are more thoroughly recrystallized, and we have biotite, muscovite, cordierite, andalusite, and quartz. So cordierite forms ovoid crystals with irregular outlines and numerous inclusions. So in this case, we have inclusions of biotite, muscovite, and opaques. So the biotite and muscovite inclusions often retain the orientation of the slaty cleavage outside the cordierite, and this indicates that the growing cordierite crystals envelope aligned micas that grew during the regional event. So if you remember, we talked about how this particular event has overprinted a much earlier regional event, and this is excellent textural evidence for the overprint of contact metamorphism on an earlier regional one. So the micas outside the cordierites are larger and more randomly oriented, suggested that they formed or recrystallized during the later thermal event. Because in our regional event, we had aligned micas, but now in this event, we have more randomly oriented micas. So this further emphasizes the overprint effect that it has had. And andalusites have fewer inclusions than cordierite, and many of them show the cruciform pattern of fine opaque inclusions known as chiastolite. Last but not least, in the inner zone, it is thoroughly recrystallized and it has lost all foliation. So both andalusite and cordierite are minerals that are characteristic of low pressure metamorphism, which is the case of the Skiddaw-Oriole, where heat is carried up into the crust by the granites. So the rocks of the inner zone at Skiddaw are characterized by coarser and more thoroughly recrystallized textures because of this heat. And the same mineral assemblage as the middle zone is seen here. So some rocks are schistose, but in the innermost portions, the fabric loses the foliation. So the rocks are typical of hornfelses. So no foliation. No to little foliation. So as you can see from the previous few slides, we can see that the zones here at Skiddaw, which were determined by Rastal in 1910, were determined on a textural basis. If we were to go on a more modern and appropriate approach, it would be to conform to the practice used in regional examples discussed previously, which is to use the sequential appearance of minerals and isogrades to define these zones, like we've done with the Barovian sequence, with the Buchan type sequences, because this is the common approach for all types of regional and contact metamorphism. But with Skiddaw, however, the sequence of mineral development with grade is pretty difficult to determine accurately. So therefore, especially for this area, a textural zonation appears to be more useful and would also be useful in perhaps some other areas of contact metamorphism. So again, this emphasizes that while we do have defined zones and defined approaches to discuss the different types of zones in different metamorphic areas, it's important to focus on the observations that you find at a specific area and deduce how to best present that information. So in this case, the best way to talk about it would be as textural zonation instead of talking about the sequential appearance of minerals like in Barovian sequences. We finally made it to our fifth and last example of the day, which is the contact metamorphism and skarn formation at Crestmore, California. And this is our final example because it is pretty interesting. It is a completely different protolith and it has unusual metamorphic conditions. So, the Crestmore Quarry is part of the Los Angeles Basin, which is made of quartz monzonite porphyry of an unknown age, which has intruded into magnesium-bearing carbonates. Could be about late Paleozoic or Triassic. So as with previous examples, the country rocks here have experienced an earlier regional event and are now mostly brucite-bearing calcite marble. So, how is Crestmore unusual? So first of all, we have the temperature attained in the inner aureole is exceedingly high for such low pressures. So it is a high temperature, low pressure system, which is typical of contact metamorphism, but the temperature being exceedingly high is an example of pyrometamorphism. So the word pyro here means fire, which refers to this exceedingly high temperature. Secondly, Crestmore Quarry is operated by a cement company, so virtually all of the aureole has been removed to supply cement for building in LA. So therefore, the data discussed in the next few slides is an occurrence that cannot be observed and studied further today. So fortunately, Burnham in 1959 mapped the following zones and mineral assemblages. So we can see here that there is a variety of minerals, and he's defined these zones as the forsterite zone, monticelite zone, vesuvianite zone, and garnet zone. And this is a sequential development of index minerals, and you have these minerals highlighted in each zone. And if you're like me, the list of zones at first is quite confusing. And this again serves to illustrate a pretty common problem faced by petrologists and probably all scientists. We can collect quality data. So as Burnham has done in the previous slide, they've had really comprehensive data on the different types of minerals. However, we can be quickly overwhelmed by the quantity at times, and it's often difficult to recognize any meaningful patterns. So here we have an idealized north-south cross-section through the quartz monzonite and aureole at Crestmore, California. So the list of minerals wasn't that helpful, and the cross-section of the area appeared to be complex as well. So what kind of approach can we take to describe the metamorphism that has happened in Crestmore, California? So here are two approaches that have been put forth by Winter in his textbook. So the first approach is to look at the minerals. So mineral associations in adjacent zones vary by the formation of new minerals as the grade increases. And it is important to note that minerals do not just occur. They don't just appear out of nowhere. So new metamorphic minerals are formed from lower grade mineral assemblages because the lower grade assemblage becomes less stable, and then the new alternative one as the grade increases. And this can only occur by a chemical reaction. So in chemical reactions, some minerals are consumed and others are produced. So for example, the step from the first zone to the second zone would be as follows. And the formation of vesuvianite zone involves the reaction below. So this shows that there is a chemical reaction involved going between these zones. So when we address isogrades as reactions instead, we can then turn to what variables are involved. So in the present case, we discovered that the majority of these prograde reactions consume SiO2. So since quartz isn't found in the Cresmor aureole, the SiO2 must be added in the form of dissolved silica in hydrothermal fluids. So we can thus conclude that the diffusion of silica from the monzonite into the country rock must play a critical role in the aureole development. So you can see here the SiO2. The second approach to trading this accumulated data is to display it in simple, useful ways. So if we are thinking of the aureole as a chemical system, we note that most of the minerals consist of the components CaO, MgO, SiO2, CO2, and H2O, with minor Al2O3. So we can graphically plot the minerals on a triangular CaO, MgO, SiO2 diagram to get a fairly simple view of how these minerals are related chemically. So these are called chemographic compatibility or composition paragenesis diagrams, and they're very useful in helping us to understand the mineral assemblages in metamorphic zones. So here we have our CaO, MgO, SiO2 diagram at fixed pressure and temperature, showing the compositional relationships among the minerals and zones at Cresmor. These numbers correspond to the zones listed previously in the text between 1 to 10. So what's happening here is that silica-saturated water escapes the porphyry, which permeates the silica-free marbles, and a gradient in silica content results in the diffusion. So the silica reacts with the carbonates to produce skarn, consisting of calcium magnesium silicates, while CO2 is liberated by the reactions. So the porphyritic nature of the pluton thus supports the idea of this fluid release. The zones at Cresmor could have formed at constant temperature and reflect a diffusion gradient in Si2 only. This is probably not the case, however, since temperature should also increase towards the pluton. So there's an increase in temperature towards the pluton. So only by knowing the pressure temperature stability ranges of the minerals and the pressure temperature dependence of the reactions relating to them could we fully understand the processes happening at Cresmor. So here is the CaO, MgO, SiO2 triangle again, but I've also helped to list the numbers and the different zones on the left of the slide for your reference. So the takeaway point from this particular example is that we can be really good at collecting lots of detailed data and really comprehensive observations, but it is more useful for us to convey that information in a way that is understandable by people, and you can convey the information in a useful, easy to grasp manner. And that concludes our particularly long lecture on the different examples of metamorphism that you can find in the field. So we've gone from the Barrovian sequence in the Scottish Highlands, and then we had a look at the burial metamorphism in Otago, the paired metamorphic belts in Japan, and we look at the Skiddaw aureole in the Lake District. And last but not least, we went to Cresmor, California to have a look at how important it is to present data in a way that is understandable and meaningful to other researchers. And next in this lecture series, we will be having a look at the different types of metamorphic rocks and how you would go about naming them. So the classification of metamorphic rocks is coming up next in part 5. Thank you again for your attention, and if you have any questions, feel free to ask them. Alright, so that is it for this lecture. Thank you again, and I'll see you next time.